Okay, I have a demo part of this as well, but maybe I'll stop displaying the slides afterwards. So maybe a hands up, who was not at the platform engineering workshop? Because I think there's a few new faces. Okay, quite a few new faces. Okay, so we should introduce ourselves. So this talk is about running LLMs on Kubernetes. We have about 20 minutes, so we're not going to be able to go into the detail and everything. My goal here is to place the parts of such an architecture in your head so that when you go maybe to do it yourself or with a customer, that you know, okay, for this, it might be interesting to apply this technology. We have platform, or Kubernetes is a platform for developer platforms, but it's also becoming very popular for AI. In fact, this is a quote from DevOps Digest saying that for those who are running Kubernetes, 2/3 of them are roughly running some AI workload on Kubernetes. And Gartner is also mirroring the same thing. So the question is, if you wanted to deploy AI workload on Kubernetes, how would you do that? For introductions, my name is Kevin Nash. I'm a solution architect. I'm also part of the container field community and the dev champion field community. I come from Ireland, the West Coast. I was just there last week. I thought I'd avail of the opportunity to show you the waves after a storm on the West Coast. So I encourage you to go if you get a chance. I'm here today with my colleagues, Magda, who's also a solution architect, and Kumadan, who's a ProServe consultant. So the first thing that I would say to you, if you're thinking about running AI workload in Kubernetes, is we at AWS, we work backwards from the requirements of our customers. And you have to listen to those requirements and decide, okay, what do they want? And is that built already? So if you're looking for a serverless LLM, then you would be thinking of direction Bedrock. So just see if those pieces are already built, because you don't want to rebuild something that exists already. Don't reinvent the wheel. But if you had to deploy LLMs on Kubernetes, you'd be looking at an architecture. This is one possible architecture that you could implement. We're going to go through, again, high level each of these pieces, so you get a feeling for what each of those components are, but not in detail about them. So the first thing that we need is a Kubernetes cluster. On AWS, the choice here is EKS. So there's two things that I would like maybe to mention with EKS. One is that we work with the upstream open source Kubernetes. We do not fork it. So what we take is upstream Kubernetes and wrap it in support for AWS services, so that you can have like a full Kubernetes experience on AWS. So if your application runs in vanilla Kubernetes, you can run it on EKS. The second thing is there's two basic options of running Kubernetes. One is self-service and the other is auto mode. And this is what you have on the left and the right of the screen. In both of those, you have a managed control plane. So we manage the control plane. It scales across multiple AZs. It's highly available, reliable. In both cases, you have that. But for auto mode, on the left-hand side here, we manage capabilities for you as well. So if you wanted to use Carpenter, if you wanted to use Argo CD, we would manage that on your behalf. And I would suggest, if you're thinking about deploying AI models on EKS, on Kubernetes, then you have enough on your hands. So the left-hand side is the easier of the two. So great, we have a cluster that is provisioned. Now we want to provision the data plane. So these are the EC2 instances, the VMs that you will run your workload on. With AWS, we have quite a collection of EC2 instances. We have, every time I look, it's increasing in number, but it's 800, 900 plus. And for accelerated compute, which is what you need to run LLMs, we have a range of EC2 instances for you, ranging from general purpose GPUs with NVIDIA to our own bespoke silicon. So we create our own chips, And that's what you see here with Inferencia and Trainium. They are our own AWS ML chips. And what's interesting about those, if your large language models support those, you can run at a higher performance for lower costs. So it's something to keep in mind if you run an AI on EKS. Now we have those EC2 instances, those VMwares, those VM instances. You want to be able to support all the AI stack on those. So how do you do that easiest? You can use our pre-baked images, bottle rock images, we call them, where you have an optimized OS, you have advanced networking enabled, you have support depending on the EC2 instance type you choose, either for the NVIDIA stack or for our AWS stack. So there's no need for you to go and create these images yourselves. You can just simply go ahead and use Bottle Rocket, and if you use an EKS Automotive, those images will be automatically selected by default. Great, so we have our images. Now we want to deploy workload onto the data plane. And again, the easiest way to do that is with Carpenter. So Carpenter, what we see here is that it will look at your pod deployment description. We have a description here of GPU. We want 1 GPU, we want 200 megabytes of memory, and then a certain amount of CPU. Carpenter will look at that, will match that to its node pools, and provision on demand. So if that EC2 instance is not available, it will provision on demand. It talks directly to the EC2 Fleet API. In a couple of seconds, a maximum minute, you have an EC2 instance available for you. What's also nice about Carpenter, it will consolidate. So if it sees that your data plane workload has been underutilized, it will reduce the number of nodes automatically for you. Great, so the Kubernetes cluster, we have our data plane. Now we start looking to deploying workload onto that. And that's basically our models. So the first thing we need is a container registry. We're deploying onto Kubernetes, we need a container. And for that we have ECR, Elastic Kubernetes, Elastic Container Registry. You can proxy other container registries if you so wish. For example, GitHub if you have upstream repositories. Then we want to deploy the model onto those images. So what would that involve? It'll involve a number of parts. First of all, you have to load the model. You have to load the tokenizer. Then when you're serving requests, the models don't speak the same language as us, so we convert those texts into vectorized tokens. We send that to the models for inference. The model comes back with the response. We have to decode that. So that's high level how LLM works. If you wanted to implement that yourself, well, what would you need? You would need the runtime. You would need Hugging Face transformers if the model was Hugging Face. You would need the model itself, the weights, the configuration of the model, and some app, some way of integrating in with the model. And you could bake that into an image yourself. And this might be interesting for prototyping or for trying to figure out, okay, how does this actually work? But it might not be the best use of your time. And to accelerate that, you could instead use pre-baked containers that we make available for you. So these are deep learning containers, and they already have some of the important frameworks ready for you to use. And so framework support, we have the likes of TensorFlow, we have the likes of PyTorch, and then those machine learning libraries that those frameworks need are also supplied in those deep learning container images. And also support for other open source inference capabilities. So if you wanted to deploy yourself on a container, I would encourage you to start off with deep learning containers. But there's an easier way to do things. And this is where we move on to inference engine. So, you know, I like to think of this as in the days when we were deploying web applications. You could implement the serverless spec. Who has worked with the serverless spec before? Who's aware of what it is? So a couple of hands. Serverlet. So when you serve HTTP requests, it will give you. So there's a couple of hands, but there's a good reason why we're probably not overly familiar with it. It's because we don't implement that ourselves. We use the likes of Apache, or we use Tomcat maybe, which is embedded in Spring Boot. And the same way for serving large language models requests, we have inference engines. And these offer out-of-the-box capabilities for us, such as better GPU utilization, better memory application. If you have larger language models that require multiple GPUs, the coordination of all that, so model sharding across multiple GPUs. And also you have significant improvements in throughput and time to first token responses. And if we see here on the right-hand side, this is an example. It's a blog that was recently published by us. The link is underneath. And you can see if you take GPT, open source, and you deploy it just as is out of the box, compare that to the throughput that you would get deploying on an inference engine, in this example, VLLM. You have almost an order of magnitude difference. So it's definitely a lot of interest for you to consider using a VLLM. And we see the same thing played out in terms of time to first token, a dramatic reduction in the time to first token. So up here on the top right of the screen, we have the LLM deployed, we have the VLLM inference engine, but we can go one step further. What about if you have a scenario where you wanted to use multiple models? What about if you want to do routing between different models? If you want to have zero downtime between model upgrades? If you wanted to integrate the whole data training and inference lifecycle into your Kubernetes cluster. And this is where you use an inference framework. And Ray is one of these inference frameworks that's quite popular and used widely. It's not the only one. And what you would do is you would run your model on a VLLM instance on your Ray cluster. So great. So this means that now you have a model deployed and running, but there is one other question that it would have. So, like when you think about these large language models, what strikes you about them?
Protocol compatibility.
Protocol compatibility, yeah, that's definitely one thing. VLM would support there between different models. But something even more basic than that.
Their size, how long they take.
Exactly. The size of the models. Those images are a bit big, aren't they? They're in fact they're massive.
In particular, when you consider everything that you mentioned before, is that baked into a single one, or?
This would be this. I'll come to that in a second. Yeah. So those images are big, and why are those images big? Well, I think it's probably quite straightforward. It's due to the evolution of machine learning. We started off with classic machine learning, with like maybe 1 million parameters, 1 million weights associated with those parameters, so you have 100 megabytes in size. And this has evolved through neural networks, through diffusion models, small language models, large language models. And you can see when we get up to the hundreds of gigabytes size for large language models, this of course means that that your actual container size is also extremely large, hundreds of gigabytes. And in this case, what we recommend is that you could deploy everything in one container, model and everything, But you can imagine your pull times, even if you had a fiber optic network, it still takes quite a while. So there's a number of ways of approaching this, and I'll show you one in my demo. One is that you can separate, and this is what we recommend, the application code, which is with the VLLM, the Python runtimes, from the model itself. And you can put the model weights on an S3 bucket. And here you have the example of it being mounted via an init container, but it's not the only way to do it. You could have a Kubernetes job pre-populating the S3 bucket. If you wanted higher performance in terms of I/O, you can use our block storage, EBS, to host the model. And if you wanted to share that model across multiple instances, you could use a file storage. In this case, the example is Amazon FSx storage. So we've taken you very quickly on a story of deploying a Kubernetes cluster, provisioning the data plane, putting those models onto inference engines, being enterprise ready with Ray, optimizing the container size. So let's look at that in reality. How would a demo of that look like? And that's what I have for you here. And I'll show you it working in a second. So we have an EKS cluster. The front end, we have a web GUI. So this is your own ChatGPT, if you like. That is exposed. The model itself is exposed via a Kubernetes service. Ray is deployed via a Ray operator. And the Ray is a distributed system. So you have a head, which is the controller, and then worker nodes, which take on your AI workload. In our case, it's deploying a Minstrel open source model, being pulled from ECR, and the weights themselves being mounted in via S3. So let us stop this presentation for a second and look at that in reality. Super. And when I change over to you see that as well. Okay, so I just want to briefly show you what that looks like when it's running. So this is our EKS cluster. There's a lot of things you have in your EKS cluster console. For example, here we know we're running on version 1.3.4. We have upgrade insights if we want to upgrade to 1.3.5. In particular, if we look at our compute here, it's been managed by Automode for you. So you didn't go and deploy these EC2 instances. They were automatically done for you. We have a general purpose node pool, which comes by default, but because we're running GPU workload, I created a GPU node pool for our AI workload because that's expensive compute. We don't want to share it maybe with general purpose applications. And if we look, let me see. If we dive a little deeper, maybe we look at we go to the cluster itself. We can see those. This is K9S, by the way, so anybody who hasn't used this for Kubernetes, yeah. Yeah, it's nice, all right. So we can see those very same nodes that we have displayed on the console. We can see them here via K9S. Those LLM services are exposed here. So we have the GUI that we're going to interact with, and we have VLLM itself. So let's look at the pods, and I have port forwarding on the open web, but let me do port forwarding also on the service. 8265. So that will give us access to our Ray dashboard. You could also expose these via load balancer, application load balancer, if you so choose. And we can see here what we had on the architecture diagram is a cluster and then a cluster head and a worker node. And if we dive deep into the worker node, we can see there's our large language model, Minstrel, running on the worker node. And then we can access hopefully, the model itself. Let's see if the port forwarding is working. Yeah. So, always demo effects, no stress. So here we have our interface into the large language model. Does anybody have a question for it? If you don't, I have a question. No question. I actually I've seen this, that you can actually even record yourself. So tell me about surfing in Ireland. So it's gonna. It's pretty good surfing in Ireland.
Pretty cool.
You just need a wetsuit. Okay, so it's translated. A noble endeavor. Yeah. So of course there's great surfing in Ireland. Yeah, and then this works the exact same way as the large language models you've been used to, except it's running under your control on your Kubernetes cluster. So hopefully, it was a very quick tour, but now you have the pieces of an architecture. If you want to deploy a large language model in a Kubernetes cluster in your head, I want to leave you with two things. One of them is a series of resources. I would recommend in particular this one here. I recommend them all, but in particular this one. These are workshops that we run virtually every week now. So if you want to get hands-on with an EKS cluster on your own AWS account for a period of time and get to talk with solution architects or even the service teams, they're very useful resources. We've also what I've shown you deployed. We've also released the code for that. It's possibly on one. It'll be linked into one of these URLs. And sorry, is there still? Please. Okay, so listen, it was a pleasure speaking to you. Thank you very much for your attention.